Yeah. Okay. All right. So we were talking about vector bundles and connections on vector bundles. So last time we saw that so we finished with this proposition that given a connection nabla on a vector bundle, we got a notion of covariant differentiation of sections along curves, right? So if we had a curve gamma in our manifold M, then a section of the vector bundle along gamma was a map sigma defined on the same interval as gamma, mapping into the vector bundle, such that sigma of t was an element of the fiber at gamma t, E of gamma t. Okay. And then there was a unique linear map, the covariant derivative, capital D sub dt, from sections of E along gamma to sections of E along gamma. Sigma goes to capital D sigma dt, which satisfied the Leibniz rule and was compatible with the connection nabla, in the sense that if sigma was given by the restriction of a global section of E to gamma, so sigma is equal to S composed gamma for some section S of E, then capital D sigma dt was nabla sub gamma prime T of S. Okay. So we proved the existence of this covariant derivative and gave a formula for it. Okay. In terms of a local basis of sections. So now we can define what's called a parallel section. So a section sigma along the curve gamma is parallel if its covariant derivative is 0. So d sigma dt is identically 0. Okay. So let's see what this looks like in local coordinates. This equation d sigma dt equal to 0. So if I take local coordinates x1 to xn on my manifold and a local basis of sections Sj for the vector bundle. So in these coordinates, if I look at the coordinate phi composed with gamma, so then this becomes a curve in Rn with coordinates x1t up to xnt. Okay. So then gamma prime t becomes sum over I, xi prime del del xi. And so d sigma dt identically equal to 0 means what? If sigma is equal to summation aj sj composed with gamma, then we know that d sigma dt will be sum over j, aj prime sj composed with gamma plus aj into nabla sub gamma prime of sj. Now nabla sub gamma prime of Sj will be what? By linearity of the connection in the first variable, that will become a sum over I, xi prime, and then you'll get nabla del del xi of Sj. So that, remember, we can write in terms of the coefficients of the connection or the Christoffel symbols, gamma ij k. So that will become a sum over k, gamma ij k into sk, both of these composed with gamma, right? Okay. And so now what you can do is take this sum over k outside, and then you get that this becomes a sum of sk composed with gamma into these coefficients, ak prime plus sum over I sum over j, xi prime into gamma ij k composed with gamma into aj. So this is equal to 0. And since the SKs are a local basis, that means that each of these coefficients is 0 for k goes from, oh, there's bad notation here. K is also the rank of the vector bundle. But anyway, so sorry about that. So then this becomes for each k, ak prime plus sum over I, sum over j, xi prime into gamma ij k composed with gamma into aj equal to 0. So this is a system of first order linear ODEs, right, on RK. Right, this is a system of first order linear ODEs in A1 to AK, which are the coefficients of my section, right? And so therefore, this has a unique solution on all of the interval of definition, given any initial condition. Okay. And then
hello. In the second, I mean, in the penultimate line, at the end, it is SL composed gamma, right?
Yeah, I was using an
L, yeah, over
L. Well, I suppose I changed the K to an L, right? It should be, it's an L, yeah. Sorry, yeah, when writing the notes, I K first, then I changed it to L, yeah. So that's why it looks so bad. Sorry about that. Yeah, this should be an L, yeah. Right. So, because
but
otherwise
SL composed gamma at the end,
right? Right, yeah. That's gamma ij oh, right, yeah. No, the over here you mean in the pen, yeah, SL composed. Yeah, right. Yes. Yeah. Right. So the point is, these are a system of first order linear ODEs, right? In A1 to AK, which are the coefficients of my section sigma. So this will have, so this was on an interval J inside the domain of gamma, such that gamma of this interval J is contained in a good open set U, where I have coordinates x1 to xn, and I have a local basis, right? All right, so this U is the domain of a trivialization of my vector bundle and the domain of a chart, right? Okay. Now, what you can do is cover the whole interval I of definition of gamma by such small, finitely many such small intervals J, right? And then on each such interval J, you have a solution defined on the whole interval J. The point is that for linear ODEs, the solutions are defined as long as the coefficients of the ODE are defined. Okay. This is not true for nonlinear ODEs. Nonlinear ODEs, the solutions are just local. They may not be defined on the whole interval where the equation is defined. Right. But the point is, since these are linear ODEs, the solutions will be defined on the whole interval J. And so then you cover the interval I by finitely many such intervals J1 to Jm, and you can glue together the solutions on each of these intervals Ji to get that for any curve gamma on a closed interval AB mapping into M, and for any T naught in I, if I take any vector V naught in the fiber at gamma T naught, then there is a unique parallel section sigma along gamma such that sigma of T naught is equal to V naught. Right. So the existence follows because we have existence to this equation of being parallel, d sigma dt equal to 0. And the solution is unique. So therefore, this parallel section that we get is unique. So is this clear?
Yes, sir, it's fine.
It's fine. Okay. So now, since the covariant derivative d sigma dt is a linear map, so if sigma 1 and sigma 2 are parallel sections, then so is their sum, right? ddt of sigma 1 plus sigma 2 will also be 0. And also any scalar multiple of a parallel section will be a parallel section. So the set of parallel sections along gamma forms a vector space, which we denote by P of gamma. Okay. Now, what does the above proposition here imply? It implies that if I take any T naught in the interval I, then if I look at the evaluation map, let's call it capital phi sub T naught. So this goes from the space of parallel, the vector space of parallel sections to the fiber at gamma T naught. So it's just the evaluation at time T naught. Sigma goes to sigma T naught. Then this map is linear and it is an isomorphism. Because, well, it is onto, because we know that for any element in the fiber, there exists a parallel section whose value at that time T naught is equal to that element of the fiber. So this map is onto, and this map is 1-to-1 because that parallel section is unique, right? Is it clear? Yeah, so the existence in this proposition gives you the surjectivity, and the uniqueness gives you the injectivity. So therefore, this map is an isomorphism. Is that clear?
Yes, sir.
Okay, so it follows that the dimension of the space of parallel sections is equal to the dimension of the fiber, which is the rank of the vector bundle K. Okay. So the space of parallel sections is finite dimensional, of dimension equal to the rank of the vector bundle. Okay. So now we can define what's called parallel transport with respect to the connection. So that's the following collection of maps. So let S and T be 2 times in the interval I. Then there is a parallel transport map along gamma from gamma S to gamma T. So this is going to be the isomorphism. Let's call it P S comma T. So this will be the evaluation at time T composed with the inverse of evaluation at time S. Capital phi sub T composed capital phi sub S inverse. So capital phi sub S inverse will go from where to where? It will go from the fiber at gamma S to the space of parallel sections P gamma, and then phi sub T will go from P sub gamma, P gamma back to the fiber at gamma T. So this composition will be a map from the fiber at gamma S to the fiber at gamma T. Is this clear?
Yeah.
So this will be an isomorphism from the fiber at gamma S to the fiber at gamma T. Okay, so in the picture, you have this is, say, gamma S. This is gamma T. And all you're doing is the following. So given a vector V here, in the fiber, right? You choose a parallel section, sigma, so that this is sigma of S, right? Okay. So sigma, there is a unique parallel section, right? Such that V is equal to sigma S. So you take this parallel section and then you look at the value of this parallel section at time t. So this will be W equal to sigma t. Okay. So this, by definition, this is your parallel transport map, PST, applied to V. Is this clear? Okay. Yeah. Is the definition clear?
Yes, sir.
Okay. So you take a vector V at time S at the fiber, in the fiber at gamma S. You take the unique parallel section sigma, whose value at time S is equal to V. Then look at the value of sigma at time t. That gives you the parallel transport of V from gamma S to gamma t. Okay. So using this parallel transport, we can get a nice basis of sections along the curve. So how do we do that? Well, what we can do is we take a basis of one fiber, say gamma T naught. Okay, say a basis EJ of gamma of the fiber E gamma T naught. Then we will get a basis capital EJ of the space of parallel sections, right? Such that capital EJ at time T naught is equal to little EJ, right? Yeah. Because since the evaluation at time T naught is an isomorphism, right? The basis EJ of the fiber at gamma T naught corresponds to a basis capital EJ of the space of parallel sections, right? Okay. And since the evaluation at any time T is also an isomorphism, evaluating the EJs at any time T will give you a basis of the fiber at gamma T, right? So in this picture, if I start with a basis at one fiber and I parallel transport them, right? So if you take a basis E1, E2 up to En or Ek, then you'll get a basis by parallel transporting them. Right, so this is at say time T naught, and this will be at any time T. This basis will be EJ of T. Okay. So this little EJ is EJ of T naught. Okay. Yeah, so you take one basis and then by parallel transporting it along the curve, you'll get a basis at every point along the curve. Is that clear? Yeah.
Yes.
So EJ of T, J between 1 and K. This is a basis of the fiber at gamma T. Yes, this is for all T. So this is where capital EJ is a basis of the space of parallel sections P gamma. Yeah. Okay. So that's the picture. Now it's useful to write any section along gamma. We can write in terms of this parallel basis. And in terms of the parallel basis, the covariant derivative will become very simple. So first of all, we need to be sure that we can write any section with respect to the parallel basis, that when we do so, the coefficients are going to be smooth. Right? A priori, it's not obvious that I know that pointwise I can write any vector in the fiber as a linear combination of these basis elements, right? Ej of t. But I also want to say that if sigma is a smooth section along gamma, then the coefficients of sigma with respect to Ej are going to be smooth also, right? They're going to be smooth functions. So I know that the coefficients of sigma with respect to any local basis Sj of E by definition will be smooth, right? So I want to say that the coefficients with respect to Ej will be smooth. So the way to do that is the following. You take a local basis Sj, then I know that my Ej's, these are solutions to a linear ODE with smooth coefficients. So the Ej's are smooth sections, right? Okay, the Ej's are smooth sections. So each Ei I can write as a linear combination of the Sj composed with gamma into some smooth functions, Aij of t, right? So Ei I can write as sum over j, Aij into Sj composed with gamma, where this matrix Aij, right? This is a smooth matrix valued function from the interval j. So j is a subinterval of I as usual, so that the image of j under gamma is contained in a chart where we have a trivialization. This is a smooth matrix valued function on the interval j, and moreover it takes values in GLKR, right? Because the Sj's are a basis and the Ei's are also a basis, right? So when you write one basis in terms of the other, this change of basis matrix is going to be invertible, right? So because it's invertible matrix valued function, its inverse, pointwise inverse, is also going to be a smooth matrix valued function. So A inverse will be, say, some matrix Bij. And then in terms of the inverse matrix, we can write the Si composed with gamma in terms of the Ei's as summation Bij Ei, where now the Bij's are smooth functions. Okay. So I've written my local basis Si composed with gamma in terms of these parallel sections Ei with some coefficients which are smooth functions. Therefore, if I take any sigma, I can write sigma. So if sigma is a smooth section along gamma, then first of all, I can write sigma as a linear combination of the Si composed with gamma with coefficients which are smooth functions by definition. And then the Si composed gamma, I can further write in terms of the Ei's with coefficients which are smooth functions. Therefore, it follows that sigma is a linear combination of the Ei's with coefficients Ai which are smooth functions. Is this clear? Yeah. Okay, so this was just to justify that the coefficients of any smooth section along gamma with respect to the basis of parallel sections will also be smooth functions. All right. The coefficients will be smooth. Okay. Therefore, when I take the covariant derivative now, if I write sigma as summation Ai Ei, then when I take the covariant derivative, d sigma dt by the linearity and the Leibniz rule, this will be sum over I. So by the Leibniz rule, I'll get Ai prime into Ei plus Ai into dEi dt, but the Ei's are parallel. So dEi dt vanishes, right? So this becomes simply sum over I, Ai prime Ei. Is that clear? So what does that mean? That means with respect to my basis of parallel sections, the covariant derivative just becomes the ordinary derivative little d dt of the coefficients, right? Is that clear? Yes? Okay. Is this clear? Yes?
Yes, sir.
Clear. Yes.
Yeah. Okay. All right. It's just from the Leibniz rule, right? dEI dt is 0. So the second term vanishes. Okay. Now let's look at the parallel transport from a time t to a time t plus h. Okay. So by definition, this is going to send my parallel section ei at t. It's going to go to ei at t plus h, right? So if I look at the inverse of this parallel transport map applied to sigma t plus h, so this will give me a vector at gamma t. Then if I subtract sigma t from that, that is also a vector based at gamma t. Then I divide by h. What will this be? Well, sigma t plus h will be what? It will be sum over I, ai of t plus h, ei of t plus h. So when I apply the inverse of the parallel transport map, each ei of t plus h is going to go back to ei of t, right? So parallel transport inverse applied to this sigma t plus h, this is going to be sum over I, ai t plus h, ei of t, right? And then I'm subtracting sigma t, which is summation ait, eit. So therefore I can group these two together, and this becomes a sum over I, ait plus h minus ait, and then I'm dividing by h. So now what happens as h tends to 0, this coefficients converge to ai prime t, right, into eit. So this is nothing but capital D sigma dt. And therefore, what do we get? We get that the covariant derivative, which we use to define parallel transport, it can be recovered from the parallel transport maps. So capital D sigma dt, I can write as a limit h tends to 0. I take sigma at time t plus h. I parallel transport it back to gamma t. And then I subtract the value of sigma at t, and then I divide by h. As h tends to 0, this converges to the covariant derivative. Okay. So let me just draw you a picture here. So for example, at time t equal to 0, right? Suppose this is, say, gamma 0. Okay. And this is, say, gamma h. Okay. So here I have, say, sigma 0. Okay. And here I have, say, sigma h. Now I have my parallel, the inverse of the parallel transport map. Okay. So let me call that ph inverse. So this is going to map this vector to a vector here. Okay. Then I take the difference of these two vectors and I divide by h. Let h tend to 0. That converges to the covariant derivative. Okay. So d sigma dt at 0 is equal to the limit h tends to 0 ph inverse sigma h minus sigma 0 over H. Okay. Is this all right? Yeah. Yeah. So what does this mean? This means that if I look at pH inverse of sigma H minus sigma 0, this divided by H, this is d sigma dt at 0 plus little o of 1, right? So if I multiply by H and take things to the other side, then I get that pH inverse of sigma H is equal to sigma 0 plus H d sigma dt 0 plus little o of H, right? Yes? Okay. So this is telling us that we can recover the covariant derivative from the parallel transport map, right? So covariant derivative so also see this the covariant derivative along curves, this d sigma dt, this gives me back the connection. If I like, this gives me, say, nabla sub x of s if sigma is s composed with gamma and gamma prime 0 is equal to x at gamma 0, right? Okay, let me stop this session and start a new one. So okay, so what we see is that the connection nabla this gives me a notion of covariant derivative along curves. And the covariant derivative conversely determines the connection, since d sigma dt is nabla x of s. If I take sigma to be of the form s composed with gamma, and gamma prime, I choose gamma so that gamma prime 0 is x at the point gamma 0, right? So the covariant derivative along curves is equivalent data to the connection nabla. And this covariant derivative along curves, this is equivalent to the parallel transport along curves. The family of parallel transport maps, PST. Right, because the covariant derivative gives me parallel transport, but the parallel transport gives me back the covariant derivative, as we can see here, right? Yes? Okay. And this parallel transport is what? This is a way of identifying fibers, right? This gives me a way of identifying fibers. Is that clear? Okay, so these three are all equivalent data. So instead of giving the connection, one could in fact give all the parallel transport maps along curves that would determine the connection equivalently. Okay. So here, if I take sigma of the form some section S restricted to gamma, then this becomes so S of P plus, where P is gamma 0, plus H times nabla X S at P plus little o of H. Right? If sigma is equal to S composed gamma, P is equal to gamma 0, and gamma prime 0 is equal to X at P. Is that clear? Okay. 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 So let's continue. So using the basis of parallel sections, in fact, we can write a Taylor formula for sections in the following form. So suppose gamma is an integral curve of a vector field X on M. And suppose sigma, my section along gamma, is of the form S composed gamma, where S is a section of E, a global section, right? So then what happens if I apply nabla X of S, if I apply nabla X n times to S, right? Then this along gamma, this is just going to be the covariant derivative capital D sub dt applied n times to sigma. And this is going to be just with respect to the basis of parallel sections capital EI, this will be given by just differentiating the coefficients AI n times, right? Okay. So here nabla sub X, I can think of this as a map from sections of E to sections of E. S goes to nabla sub x of s, right? Okay. So this gives a linear map from sections to sections. And applying this n times to the section S along gamma is the same as differentiating the coefficients n times with respect to the coefficients with respect to a parallel basis, EI. So that will give us a Taylor formula as follows. So if I take S at the point gamma t plus h, and I parallel transport it back to gamma t, I take the inverse of parallel transport from t to t plus h. So then what will this be? This is going to be sum over I, ai of t plus h into ei of t, right? Because the inverse of parallel transport will map ei at t plus h goes to ei of t, right? So therefore, I get ai of t plus h into ei of t. Now I apply the Taylor formula to the coefficients. So this I can write as ai of t plus ai prime t into h plus ai nth derivative at t over n factorial into h power n plus a term which is little o of h power n, the whole thing into ei of t, right? But now each of these terms, for example, the first term, this second term here, sum over I, ai prime t, ei of t, that is nothing but nabla x of s, right? And this nth term will be nabla x power n of s, right? So what do I get? This sum will become the sum j goes from 0 to n, nabla x power j of s at gamma t into h power j, right? Plus a term which is little o of n. Okay. So that gives me this Taylor formula, right? Is this clear? Yeah, so the Taylor formula, I mean, let me just take for simplicity t equal to 0. So the Taylor formula will be that, so if I take, so gamma is equal to integral curve of x in chi m. Yeah. And then what do I get? I get that p, so let's say p is equal to gamma 0. Then I get the inverse of parallel transport applied to, so S is a section of E. So pH inverse of S at gamma H, this is equal to a sum j goes from 0 to n, nabla x power j applied to S at P into h power j over j factorial, okay, plus a little o of h power n as h tends to 0. Okay. Is this clear? Yeah. So in other words, I get a Taylor formula. S at the point gamma of h is equal to pH applied to SP plus H nabla x SP plus h squared over 2 nabla x squared s at P plus h power n over n factorial nabla x power n s at P Okay, so these are all vectors at P, and then I'm parallel transporting the sum of these vectors by PH. Okay, I'm parallel transporting them to gamma H. Okay, so I get this plus a little o of H power n. Is this clear? Okay, so this is the Taylor formula. All right. Is this okay?
Yeah, it's okay.
It's all right. Yeah. Okay. Fine. So now we come to what's called the curvature of a connection. So the curvature is going to measure the failure of covariant derivatives to commute. Okay. So what is the curvature of a connection nabla on E? So this is going to be, first of all, a trilinear map R from chi-m cross gamma E going to gamma E. So that means it takes a pair of vector fields on M, X and Y, and it takes a section S, and it gives me a new section. What is the new section? It is nabla Y, nabla X of S minus nabla X, nabla Y of S plus nabla sub bracket XY applied to S. Okay. All right. So this is trilinear with respect to X, Y, and S. And so it's trilinear with respect to the constants. But in fact, because of this term nabla bracket XY here, what one can check is that in fact it is trilinear with respect to C infinity M. In other words, these three are modules over C infinity N. So as a map of modules, it is linear, trilinear. Okay, so if I multiply X by a function F, then that F will come out when I apply R to X, Y, and S. If I multiply Y by a function F, that F will come out. If I multiply the section S by a function F, that F will come out. Okay, so I leave that as an exercise to you to check, just uses the Leibniz rule. You check that this curvature map, this trilinear map, is actually trilinear with respect to C infinity M. Okay. All right. And then once you know that it is trilinear with respect to functions, then it's easy to see that the value of Rxys at a point P, this only depends on the values of the vector fields xy and the section S at the point P. Okay, it only depends on the values of x, y, and S at P. So this is similar to when we showed that for a connection nabla, see, for a connection, the map x comma S goes to nabla XS. This was C infinity M linear in X, right? And that was enough to show that nabla XS at P only depends on the value of X at P, right? We were able to localize the connection to a point because it was C infinity M linear in X, right? So the same sort of calculation will let you show that this is only dependent on the values of X, Y, S at P. Okay. So it does not even depend on the values in a neighborhood. It just depends on the values at the point P. Okay, so I leave that to you to show as an exercise. And so it follows that for each point P in M, we therefore get a map R sub P. So this is going to be a bilinear map now from TPM cross TPM to the vector space of endomorphisms of the fiber EP. Okay. So what is this map? So you take two tangent vectors at P, V and W. Then this is going to define a linear map of the fiber to itself. So that linear map is the following. It's going to be RP of VW. So what is this? This takes a vector Z in the fiber EP and maps it to RP VWZ. How is this defined? RP of VWZ. This is defined to be R of XYS evaluated at P, where XY are vector fields on M and S is a global section of E, just satisfying that X at P is equal to V, Y at P is equal to W, and the section S at P is equal to Z. Okay. So this is well defined because the value of RXYS only depends on the values of X, Y, and S at P. Okay. Therefore, this is well defined. Is that clear? Okay, so the curvature, yeah, any question? Any questions? Yeah. Okay, so the curvature is now giving a bilinear map from the tangent space cross itself to the space of endomorphisms of the fiber. Okay. And this map, you can easily see it's alternating in V and W, right? Because if I interchange X and Y here, then this changes sign, right? R of XYS is equal to minus of R of YXS, right? If I interchange X and Y, then this changes sign, right? Is that clear?
Yeah, it's clear. Yeah.
Yeah. So therefore, this bilinear map is actually an alternating bilinear map. Okay. So at each point, I get an alternating bilinear map from the tangent space cross itself to the space of endomorphisms of the fiber. In other words, this curvature R, this becomes a section of a bundle. What is the bundle? It is the bundle of two forms, wedge squared of T star M, tensor with endomorphisms of the vector bundle E. Right? Okay. So this is what's called an endomorphism valued two form. Right? It's a two form, but with values in endomorphisms of the fibers. Okay. So you can see this as a section of, so endomorphisms of E. I know that pointwise endomorphisms of the fiber, remember we did this isomorphism right at the beginning. This is identified with the dual E star tensor E, right? Yes? Right, remember we showed that HOM of VW was identified with V star tensor W, right? So,
Yeah.
So endomorphisms is E star tensor E, and here I have this wedge squared T star M. So this becomes a section of wedge squared T star M tensor E star tensor E. Okay, so that is what this object is, this curvature. It's a section of an associated bundle. Okay. Is that clear?
R is a two form actually.
It's an endomorphism valued two form, right? It's not a
Okay.
scalar valued two form.
Yeah. Right.
It takes values in endomorphisms. That's why I need to tensor with the endomorphisms.
Yeah.
If it was scalar valued, then it would be just wedge squared T star M. But since it's taking values in endomorphisms, I need to tensor with endomorphisms.
Endomorphism. Okay.
Makes sense, yeah? Okay.
Yeah. Thank you.
So it's an endomorphism valued two form. It's an endomorphism valued two form. Yeah. So all this might seem a bit abstract. More concretely, actually, how do you get the curvature operator, this endomorphism, how do you get this endomorphism? We can get it from parallel transport in the following way. So let VW be two vectors in TPM. And now you can choose vector fields XY near P such that they commute. So the bracket of XY is 0. So their flows commute, remember, right? And so that X at P is V and Y at P is W, right? We can always choose two such vector fields XY. Now let phi T and psi T be the flows of XY, okay? Then for T positive, I can form a quadrilateral gamma T. So it's a closed curve made up of segments of integral curves of X and Y. So what do? I start with P. I flow along the flow of X for time T, right, to get a point P1. Then I flow for time T along the flow of Y to get a point P2. Then I flow along the flow of minus X. So I apply phi minus T to get a point P3. And then I flow along the direction of minus Y. Okay. And that will bring me back to P because the flows phi T and psi T commute. I've chosen XY so that their bracket is 0. So when I do X for time T, then Y for time T, then minus X for time T and minus Y for time T, that will bring me back to where I started, right? Yes? Because the flows commute. Yeah. This is just the composition of, phi T, and then I apply psi T, then I apply phi minus T, which is the inverse of phi T, and then I apply psi minus T, which is the inverse of psi T, right? So because they commute, the psi T, psi minus T, and phi T, phi minus T will cancel, right? So I get the identity map. Okay. Is that clear? So I get a closed curve, right? Now I can do parallel transport along this closed curve, right? So I parallel transport along this segment from P to P1, then from P1 to P2, then from P2 to P3, and then from P3 back to P. So that will give me an endomorphism of the fiber at P, right? So let me call that P sub T. So this goes from the fiber EP to itself. Okay. This is parallel transport along this closed curve, gamma T. Is that clear? Okay. Then it turns out the curvature, this endomorphism, RP applied to VW, this I can write as a limit as T tends to 0 of this endomorphism PT minus identity divided by T squared. Limit T tends to 0. Okay, so this is a limit of endomorphism. So this is an endomorphism of the fiber. Okay. So is the statement clear? Yeah.
Yeah,
It's clear. Yeah.
So what does that mean? That means that basically the curvature is the following. I can write it in terms, geometrically, I can see it in terms of parallel transport. I have two vectors, say V and W. So what I'm doing is I'm flowing in the direction of V for a small time T, then W, then minus V, then minus W, like this, okay. And so this is for time T, time T, time T, time T. Okay, so this is phi T of P. This is psi T of phi T of P. And this is phi minus T psi T phi t of p. And this p is nothing but psi minus t, phi minus t, psi t, phi t of p. Okay. So this is my little quadrilateral. And then capital PT, this is parallel transport along this curve gamma t. So this goes from EP to EP. Okay. And what I have is that PT minus identity over T squared, this converges to RP of VW. Okay. So in other words, I can write this parallel transport PT as identity plus T squared into RP of VW plus little o of T squared. Right? Okay. Yeah, so notice this is saying what? That parallel transport along this small curve. So the diameter of this curve is of order t, right? So the side lengths are of order t. So you would expect that this parallel transport would be close to the identity and maybe differ by some term of order at most t. But actually what happens is, because you have a parallel transport in the x direction and then in the minus x direction, and also in the y direction and in the minus y direction, you have some first order cancellation. Okay, there are first order cancellations which occur, and what remains is a second order term. All right. And that second order term, the coefficient of t squared is exactly the curvature. Okay. All right. So this parallel transport is identity plus a second order term, t squared into the curvature plus higher order term. Okay. Yeah. So I won't prove this, but I'll share with you a note which does do the proof of this, which I wrote earlier. So it's a rather long calculation, so I don't want to do it. So I've done this calculation for a connection on the tangent bundle of a manifold. But I mean, the same proof works for any vector bundle. So let me just give you an idea of the proof. It uses the Taylor formula, okay, that we developed. So you take this quadrilateral, say it has vertices P, Q, R, and S, okay? And so you have 4 parallel transport maps, say Q1 from the fiber at P to the fiber at Q, then a Q2 from the fiber at Q to the fiber at R, then a Q3 from the fiber at R to the fiber at S, and then finally a Q4 from the fiber at S to the fiber at P. And so my parallel transport along this closed curve is the composition Q4, Q3, Q2, Q1, right? Okay. Now you take Z, which is an element of the fiber at P, and you let capital Z be a smooth section near P, whose value at P is equal to little z. Okay. Then using the Taylor formula, you can write the value of Z at Q as Q1 into little z plus nabla xz at P into T plus half nabla x z at p into t squared plus a term which is big O of t cubed, right? This is the Taylor formula. Yes? Okay. Yes? Right. And now,
Yeah.
this is the Taylor formula that we developed. And now you have z at r. So this gives me z at q. Okay, now I look at z at r. So that is going to be, by the Taylor formula, q2 into z at q plus nabla y z at q into t plus half nabla y z at q into t squared plus O of t cubed. Right? That's because when I'm going from q to r, I'm flowing along the flow of y, right? So I apply the Taylor formula with the vector field equal to y. Okay. But now in this expression here, this z at q, I replace by the first expression, which was q1 into this sum. Okay. So this will become q2 into q1 of something. Okay. And now this nabla y of z at q, this I also replace by the Taylor formula. This will become q1 of nabla y z at p plus nabla x of nabla y z at p into t plus O of t squared. Right? Do you understand? This q here I can replace by p by applying the Taylor formula with respect to the vector field x. Okay, so I'll replace this term here and also this term here. So then I discard the terms which are little O of t squared, and what you'll find is you'd get some expression of this form, q2, q1, and then you get z of, then you'll get some first order terms, nabla x z at p plus nabla y z at p into t plus some second order terms, nabla x y z at p plus half nabla x z at p plus half nabla y z at p into t squared plus big O of t cubed. Okay, and then you continue this process. So I won't do more, but it's not very difficult. You just keep following the similar sort of calculations. Okay. And so you get an expression for z of s as q3, q2, q1 of some sum. All right. Where some cancellations occur. And then finally you get little z, which is z at p, becomes q4 of something, and then you apply further calculations. And finally you get that z at p becomes my parallel transport pt applied to little z plus some first order terms which cancel. And then these second order terms, what happens is the second order terms cancel except for this nabla x, nabla y, z minus nabla y, nabla x, z. Okay. And yeah. Okay, so you bring this z to the other side, take these terms to the other side. Okay. And you divide by t squared and you get this result. Okay. So I'm not going to do this. It's a rather long and tedious calculation, but you can go through it or try and work it out yourself, and you'll see that this works. Okay. So that's the idea behind the proof of this. Okay. Yeah. Okay. So that's the curvature operator. We'll be needing this later in the course in many computations. So finally, the last thing to talk about is, what about induced connections on induced bundles? So for example, suppose nabla is a connection on E, then you get an induced connection on the dual bundle E star. Okay. So how is this connection defined? Well, suppose alpha is a section of the dual bundle and X is a vector field on M. Then you want to define nabla sub X of alpha. This is again going to be a section of the dual bundle. So how should it be defined? It should be defined as follows, that if you take a section of E, say S, well, then alpha acts on S, right? So alpha of S is going to be a function on the manifold. So my vector field X can act on this function. Now what I want is that my induced connection should satisfy a Leibniz rule. That is, X acting on alpha of S. The idea is you first differentiate alpha with respect to S and then act on S, and then you apply alpha to S differentiated by X. All right. So you should have a Leibniz rule. So this should be nabla X alpha applied to S plus alpha applied to nabla X of S. Okay, is this clear what kind of objects we have here? This nabla X alpha, this is what I want to define. This is going to be a section of the dual bundle. This can act on a section of the bundle E to give a scalar. And similarly, this alpha is a section of the dual bundle. This can act on nabla XS, which is a section of the bundle E, to give a scalar. Okay. All right. So let me finish this session and start a new one. So this is how we want to define our connection on the dual bundle. Okay. So let me stop this session and start a new one. Let's continue. So okay, so we want to define a induced connection on the dual bundle E star so that it satisfies this Leibniz rule, right? A vector field X applied to a section of the dual bundle alpha applied to a section of the bundle E. This should be, you first differentiate alpha with respect to S. So this is supposed to be the induced connection, which we want to define, nabla X alpha. And then you apply this to S plus alpha applied to, you differentiate S, nabla X S. Okay. So we need to check that this formula actually defines a connection, right? So let's see that if we had such a connection, what does it look like in with respect to a local basis, right, of sections? So suppose SI is a local basis of E, okay, then SI star I can take at each point the dual basis. That will be a dual basis of E star, right? Okay, so then any alpha I can write as sum over I, AI SI star, okay. Now my nabla X of alpha, this is going to be also sum of BI SI star, right? Okay. Both are sections of the dual bundle, so I can write them with respect to the basis SI star of the dual bundle. Okay. Now, what are these coefficients AI? AI is alpha of SI, right? If I apply alpha to SI, since SI star is the dual basis, only one term will remain, right? Which is AI into SI star of SI, which is 1. So AI I can write as alpha of SI, right? So if I look at X of AI, then what is this? This is X of alpha SI. Now my induced connection on the dual bundle, it should satisfy this property. This should be nabla X alpha applied to SI plus alpha applied to nabla X of SI, right? So this nabla X alpha applied to SI, this is going to give me BI, right? Because nabla X alpha has coefficients BI with respect to the dual basis. So when I apply it to SI, I'll just get BI. And then I have this alpha of nabla X SI, okay? So that means that my coefficients BI are what? BI is X of AI minus alpha of nabla x si. Right. And so that means that my nabla x alpha, which is summation bi si star, this should be given by sum over I x ai minus sum over j aj sj star applied to nabla x si, the whole thing into si star, right? Is this clear? I just solve for the BIs here, right? I just solve for what the BIs should be. The BIs have to be given by this formula, right? Okay. Is this clear? So the point is, I can take this equation as the definition of my connection on the dual bundle, right? I define nabla x alpha by this formula, that if alpha is of the form summation ai si star, then nabla x alpha will be of this form. Okay. And then it's easy to check that this satisfies the properties of a connection. That is, it is C infinity M linear in the first variable in X. Okay, so nabla sub fx of alpha is f nabla x of alpha. That's clear, right? If I multiply X by a vector field F, then by a function F, sorry, then that F will come out of the first term here. And this, I'll get nabla fx of si, that F will come out here. And so F will come out of the whole expression, right? So it's C infinity M linear in the first variable. And in the second variable, it satisfies the Leibniz rule. So if I multiply alpha by F, then my coefficients AI all get multiplied by F. Okay, and then a calculation, you just do the calculation, you'll get X of FAI. So that you use the Leibniz rule for X, right? And you'll find that it satisfies the Leibniz rule. Okay. Okay, so this defines a connection on the dual bundle. Is that clear? Yeah, this formula defines a connection on the dual bundle. Any questions? Is this okay? Yes, all right. Yeah. So this defines a connection on the dual bundle. Okay. So the point is that you have this equation holds that x of alpha s is nabla x alpha of s plus alpha of nabla x s, right? Our connection on the dual bundle is defined so that this equation holds. Okay. This uniquely determines the connection, right? Because see, my nabla x of s, this is already given, right? And this x of alpha s is also, I mean, this is given, right? So that means that this nabla x alpha applied to any section S of E, this is uniquely determined, right? By my nabla x of S, by my connection on E, right? That determines nabla x alpha applied to any section S. But nabla x alpha, this is a section of the dual bundle. If I know what it gives applied to any section of the bundle E, then that determines this section of the dual bundle, right? Yes. So, I mean, if such a connection exists, then it is unique, right? Is that clear? Okay. So, okay, if this seems a bit abstract, I mean, then you can think of, the connection on the dual bundle. Actually, it comes in this way also. So the connection on the dual bundle, you can get it using parallel transport. So remember, we said that the data of the connection was equivalent to the data of parallel transport, right? So here, if I take a curve gamma, right? So say I take a point P, okay, and I take, so this is say gamma 0, and then I take, this is Q is gamma T, right? So here I have sitting above this for the bundle E, I have the fiber EP and the fiber EQ here. And I have the parallel transport PT, right? Okay. Now for the dual bundle, what do I have? I have over here the dual space EP star, and I have over here EQ star, right? Now, the dual of this parallel transport map goes in the backward direction, right? From EQ star to EP star, right? Yes? Right? The dual goes backwards, right? Yes?
Yeah.
So if I want a map going forwards, what should I do? What's the obvious thing to do? If I want a map going forwards, what should I do? Anyone?
Take dual of PT inverse. Or something.
Yeah, exactly. So take the inverse of the dual, right?
Yeah.
Exactly. So take PT star inverse. Okay, so that goes forwards from EP star to EQ star, right? Yes? Okay.
Yeah.
So now, suppose I have alpha, which is a section of the dual bundle, right? I have a point P equal to gamma 0 in M, and I have a vector V in TPM such that V is equal to gamma prime 0, right? Rather, I'm given P and V, I choose a gamma so that gamma 0 is P and gamma prime 0 is V, all right? Now, I need to define nabla sub V of alpha, right? I have to define nabla sub V of alpha. Yes, at the point P. Yes. So how will we define this? I have this, what I want is that this PT star inverse, this should be parallel transport for the dual connection, right? This should be the induced parallel transport for the dual connection. So if this is the parallel transport for the dual connection, how do I get the connection from the parallel transport? I differentiate the parallel transport, right? That will give me back the connection. Yes? Right?
Yes, sir.
So this should be a limit. T tends to 0. So what do? I take my dual section alpha at Q, right? So I take alpha at gamma T. So I take, so let me write this with some more space. So define this, define nabla V alpha at P to be the limit T tends to 0. So what do? I take alpha at this point Q. So that's alpha at gamma T. Okay. Then I can apply this PT star. This will take me back to EP star, right? So I just apply PT star to this. Okay. And then this gives me an element of the fiber here. So I subtract alpha at P from this. And then I divide by T. Okay. Is that clear?
Yeah.
This will give me my connection on the dual bundle. All right. Okay. This will give my connection on the dual bundle. Okay, this PT, this is parallel transport for E. Okay, so I can use the parallel transports to define the induced connection. That's all. See, connection after all is the same as parallel transport, which is nothing but identification of the fibers. So if you're getting an identification of the fibers of E, then by taking duals, you'll get an identification of the fibers of E star, right? That's all. It's very simple. It's very simple. Is that clear? Yes? Okay.
Yes, yes.
So this will satisfy the Leibniz rule that we want, that x of alpha s is equal to nabla x alpha s plus alpha nabla x s. Okay. Yeah, I mean, how would you try and prove something like this? Like what is x of alpha s? You have to look at alpha at, well, yeah, so alpha at, so if I look at it at time, so this is alpha at gamma t applied to s at gamma t. Right. So I want to do a Taylor expansion of this. Right. So so if I do PT star of this, so I know that PT star of alpha gamma t, that is going to be alpha at P plus T times this. Okay. So that is going to be alpha at P plus T times nabla X alpha at P applied to S of gamma T. Wait 1 second. No, sorry. Yeah, I mean, it is possible to prove this Leibniz rule using this definition. It is possible. I'll have to work it out. Yeah. So. Yeah, right. Yeah. So, okay, let me not get into that now. But anyway, the point is that the connection you can define using the duals of the parallel transport. Okay. And I mean, that's one way to see it easily. But and we can take this formula that we've given here as the definition, and then I leave it to you to do as an exercise that the parallel, so with respect to this connection, the dual connection, the parallel transport for the dual bundle is given by taking the parallel transport for the bundle E, taking its dual and then its inverse. Okay. So that will show that this definition here matches with the definition given here. Okay, that will show that these two definitions agree. All right. So you start with this definition. This is a concrete definition we've given, which shows that that we have a connection. It satisfies C infinity M linearity in the vector field and Leibniz rule in the section. And then you show that for this connection, the parallel transport of this connection is given by taking the dual and the inverse of parallel transport of the original connection. Okay. So prove this as an exercise. All right. Okay. So let's work out the curvature of the dual bundle in terms of the curvature of the bundle E. Okay. So let XY be vector fields on M which commute. Okay, we want to compute curvature Rxy of some alpha, right? So we can always choose XY so that they commute, right? We know that the curvature only depends on the values of XY at the point P. So we can choose them so that they commute. So, so let's take a section alpha, which is with respect to the local dual basis Si star. It is summation Ai Si star. Then let's look at nabla y of nabla x of alpha, right? So nabla x of alpha by our definition of the dual connection, this is going to be sum over I xai minus alpha of nabla x si, the whole thing into Si star, right? Sum over I. right? This is our definition of the dual connection. Okay. Now, now applying nabla y to this, again by definition of the dual connection, means I have to apply, I take the sum over I, y applied to each coefficient here, xai minus alpha of nabla x si, minus, now I take this, instead of alpha here, I take this section of the dual bundle, which is nabla x alpha, and that I apply to nabla y of si. Is that clear? Yes? Okay.
Yeah.
Right? So this is again by definition of the dual connection. So now here this y applied to this thing, I expand. So this will be y applied to x ai minus, now I use the Leibniz rule. So y applied to alpha of some section of the bundle E is, first I differentiate alpha. So this will be minus nabla y alpha of nabla x si minus, then I'll take alpha of, so I differentiate this section with respect to y. So I'll get nabla y of nabla x si. Okay. And then I have this other term here, minus nabla x alpha, nabla y si. And then outside I have si star. Okay. So when I take the curvature of the dual bundle, Rxy alpha, what will this be? This will be nabla y, nabla x alpha minus nabla x, nabla y alpha. There is no bracket term, nabla bracket xy alpha, because I've chosen xy so that the bracket of xy is 0. Okay. So I just get this, the difference of these two terms. Now, when I take nabla y, nabla x alpha minus nabla x, nabla y alpha, basically I just have to take this expression and interchange x and y and then subtract, right? So when I interchange x and y, what will happen? The first term, yx will become xy, right? And then I'm subtracting. So I'll get yx minus xy. That is minus the bracket of xy applied to ai. But that is 0 because I've chosen xy so that the bracket is 0. So the first term will vanish. Okay. And then I look at this term, nabla y alpha, nabla x si, and I have here nabla x alpha, nabla y si. So the sum of these two terms is symmetric in xy, right? Yes, when I interchange xy, the sum of these two terms will stay the same, right? This term will become this term and this term will become this term. So the sum is symmetric. So in this difference, these two terms will vanish, right? Is that clear? Yes? Okay. So what remains? What remains is this term. So I'll have a nabla y, nabla x, si, and then I'll have a nabla x, nabla y, si, and then I have alpha applied to that. So what I'll get is minus alpha nabla y, nabla x, si, plus alpha nabla x, nabla y, si. Then that whole thing into si star, and then sum over I. So I take the alpha common. So this becomes alpha of nabla x, nabla y, si minus nabla y, nabla x, si. So that becomes minus r of xy si, right? The curvature of the bundle E applied to si. Is that clear? So I get that r of xy alpha is sum over I minus alpha of r of xy si applied to si star, into si star, sum over I. So now when I apply this to some si, what will I get? This, all the terms will vanish except for the ith term. This will become just minus alpha of rxy si. Is this clear? Yes? Okay, notice Rxy alpha this is a section of the dual bundle. This acts on SI, which is a section of the bundle E, right? So this left-hand side is a scalar. Similarly, right-hand side is also a scalar, right? This Rx, this alpha is a section of the dual bundle. It acts on Rxy SI, which is a section of the bundle, right? To give a scalar. So Rxy alpha applied to SI, this is minus alpha of Rxy applied to SI. This is true for all I. And then by linearity, what you get is that for any section S, Rxy alpha applied to S will be minus alpha applied to Rxy of S. Is this clear? Yes?
Yeah.
Any questions? Is the calculation okay?
Yeah, it's okay.
Yeah, all we used the sum of these two terms, this second term and this fourth term here, the sum of these two terms was symmetric in XY, right? So when we take the curvature, these two will cancel, right?
Yeah,
Got it. So only this term will remain. This term will give you the curvature of the bundle E, right? Applied to SI. Right? So it's a straightforward calculation. So you get this formula, okay? And the last term, the last formula is by C infinity M linearity. Any S I can write as summation AI SI. And I know that the curvature operator is symmetric, is C infinity M linear. So the AIs will come out. Okay, so I'll get this formula for any S. Okay. Okay. So that gives me the curvature of the dual bundle. And finally, to finish this section on vector bundles and connections, we can look at the induced connection on the tensor product. So suppose I have a connection nabla1 on E and a connection nabla2 on a bundle F. Then you define a connection nabla on E tensor F by nabla x of S1 tensor S2. Okay, so if S1 is a section of E and S2 is a section of F, I can look at S1 tensor S2. This is a section of E tensor F. So I define nabla x of this to be nabla1 x of S1 tensor S2 plus S1 tensor nabla2 x of S2. All right. So again, a kind of Leibniz rule. Right. So how do we compute this connection? Well, if EI is a local basis of E and Fj is a local basis of F, so then EI tensor Fj, this will be a local basis of E tensor F. And so any section S I can write as sum over Ij, Aij, EI tensor Fj, right? So then if this first Leibniz rule is to hold, then my covariant, my connection nabla x of S has to be given by this formula, right? So I'll have to have x Aij into EI tensor Fj, right? Plus the second part will be Aij into, I'll get nabla x EI tensor Fj plus EI tensor nabla x Fj. So you can take this formula as the definition of the connection on the tensor product bundle. And then you check that it satisfies the Leibniz rule. It defines a connection. Okay. And then finally, as an exercise, you could also define this using parallel transport, this connection. So that will be given by the following exercise, that if P1 and P2 are the parallel transports along gamma for E and F, then the parallel transport along gamma for E tensor F is nothing but the tensor product of the parallel transports. Okay, so P will just be P1 tensor P2. All right. P will just be P1 tensor P2. And again, as an exercise, you can compute the curvature of E tensor F. This will be R of xy. So this is an endomorphism of the tensor product, this R of xy, right? So this is going to be the curvature of the first bundle E, R1 of xy, tensor the identity. Okay. So this tensor product is an endomorphism. Okay, it's a tensor product of linear maps. So this is an endomorphism of E tensor F. Okay. And plus identity tensor R2 of xy. Okay. So where here R1, R2 are the curvatures of E and F. All right. Okay, so try and prove these exercises. Okay. Yeah, so that will give us the induced connection and also parallel transport and the curvatures of the tensor product bundle. Okay. Is this all right? Any questions?
Sir, how is the format of the midterm exam?
It will just be 40 marks. Yeah, 40 marks exam. Yeah.
Okay,
Maybe
and,
five or
and
six
the
questions.
yeah, okay. And like the questions would be asked from the exercise or the outside?
No, from the exercise. Yeah, just from the exercises and the notes. Yeah.
Okay. So whatever portions you have covered, all the
Sure.
exercises. Okay.
Yeah.
Nice.
So basic exercises and definitions and so on.
Okay.
And okay, so we should set a date for the midterm, right? So
I mean, here it's already fixed.
what is the date for the midterm?
Okay, just let me check.
Just let me know what is the date.
Yeah. Just a second.
Yeah.
It's 22.
Which is Wednesday, right?
Yeah.
What time?
Morning session 10 to 1.
Oh, so we won't need 3 hours. So we can make it 11 to 1 on Wednesday. Okay. It's a
But it would be offline, right?
How can it be offline? I mean, oh, there'll be some. I see. Someone will invigilate in Bangalore. Is that how?
Yeah, something like that. I mean, we heard something like that. We are not sure.
I mean, how will the questions, the scripts be graded? They'll be sent back to me, is it? They'll be scanned and sent to me.
Yeah, probably.
I haven't discussed this with the dean's office, so I don't know what they plan to do. Normally, I would have just sent you by email and then you would have scanned and sent me back your papers. That's what I did for previous online classes. But I mean, I don't know what the dean's office is planning, so I should ask them. Do you know? Can you ask the dean's office and let me know what the plan is?
Okay, then on Monday I will.
Yeah, just ask and email me. Let me know what the plan is.
Sure.
So, okay, 22nd from 10 to 1, we can start at 11. There's no need to start it. It'll be a 2-hour exam. It'll be a 2-hour exam.
Yeah,
So
that depends on you
Yes.
that the exam should be finished within 10 to 1. That should be held within 10 to 1.
10 to 1, you're saying, right?
Yeah, 10 to 1, that, I mean, the timing depends on you. I mean, within 10 to 1, you can take it anytime.
Yeah. So I'll take it from 11 to 1. Okay. I'll take it from
Okay,
11 to 1. I'll take it
okay.
from it. So, okay, fine. I'll probably email the dean's office the exam paper then. And then I suppose someone can invigilate in Bangalore and that should work. Yeah. Okay. So just find out if what they're planning. All right.
Sure, sir, sure.
Yeah. And let me know. Okay. So let's stop today then. And I'll see you next week. Okay.